Hey kids, so here is the lab report sheet walkthrough that I promised. I'm not going to do every question. I'm going to do a lot of the questions that I've been getting questions about so you guys can have a little bit more time with this and hopefully a little more assistance on stuff like molarity, which we haven't covered. So then I'll give you the answer, you'll be all set as long as you see this video and or you've talked to me, then you'll be all set. But in regards to these 5 labs, I want you to be thinking about, as you're completing them, think about how they reinforce what you know about moles, molar mass, empirical formula, all the stuff that you're going to be needing for the midterm and that you've needed for what we're going to do next. Be thinking about how it reinforces how you understand the mole or what you know about moles and percent error and percent composition and stuff like that. So with that, I'll read you guys the objectives of the first lab, which state that you're, let's see, what do we got? I'm not reading the same one. Okay. I promise I have it pretty well organized. I did. Alright, so I'm going to do, when I say first lab, I mean 4-1, okay? Not the order that you did them in. The only reason we did 4-1 last is because I didn't have enough magnesium, okay? If you think about them logically in order, 4-1 comes first, okay? So we're determining the empirical formula of a compound, which we need to look at for the objectives. The mass of magnesium chloride produced when a given mass of magnesium is reacted with hydrochloric acid. So I'll write up here magnesium plus hydrochloric acid, and we're looking at how much magnesium chloride is produced. Okay? So using rules about forming neutral compounds, I know that Mg, magnesium is +2 and chlorine is -1, so I have, it's drawing when I have on it, that's pretty cool. It's the first time I've used a smartboard like this. But Mg is +2 and Cl is -1, so I make MgCl2. Okay, that actually answers a couple questions in the pre-lab piece here. So this is one of the objectives, is finding how much magnesium chloride will be produced when you put magnesium and hydrochloric acid together. Another objective is calculate the empirical formula of magnesium chloride. So the empirical formula is actually looking at how many magnesium and how many chlorines are in the least possible combination of magnesium and chlorine. Okay, so you might, certainly it's possible to have Mg2Cl4. Okay, but what you're doing in this lab is trying to figure out what the empirical formula is, or perhaps in math, the lowest common multiple, the lowest common denominator. I don't remember which one I'm thinking of, but you're trying to figure out and prove that the lowest common, the least possible combination of these two elements in this compound is Mg1 and Cl2. Okay? It's also asking you to compare the empirical formula obtained experimentally with the accepted formula. So you're going to compare what you find, which hopefully is around Mg1Cl2, to what it should be, which is MgCl2. Okay? And then analyze the cause of unexpected experimental results. So looking at what might have caused your magnesium chloride ratio to be off or to be really good. Okay? Moving on, let's look at looking at some pre-lab questions. How can you tell when an excess of hydrochloric acid has been added to the evaporating dish with magnesium? Well, right here, on the very first page of the lab, it has this nice little introduction. Hopefully you guys can see it. I can put it up against like this. Maybe you can see it a little better. It talks about it right in there. It also talks about the water of hydration in here too. So for number 5, you guys can find an answer to those. And also same for number 6. So 1, 5, and 6 are right in the introduction for you to find. And if you can't find them really obviously, definitely can use Google. Those are very simple answers to find. Formula for magnesium chloride, I just told you. Using rules of neutral compounds, MgCl2. I wrote it in the wrong place. Sorry. calculate the formula mass. That's also the molar mass. So we want to know how much does magnesium weigh and how much does chlorine weigh, times 2. So periodic table, 35.45. And magnesium, 3 is good. Okay, so if we add these two together, we get, I'll get out my calculator so we get a nice exact number. 35.45 plus 24.31. So the formula mass, let's use blue. Formula mass of magnesium chloride is 95.21 grams per mole. So what that's saying is that for 1 mole, 6.022 times 10 to the 23rd molecules of magnesium chloride, 1 mole of that weighs 95.21 grams. Okay? Theoretical percentage, let's just think about what a percent is. Let me say 35.45. So the percent, let's see, we can put it right here. This equals 70.9. So our total mass, our total formula mass is 95. Oops. 95.21. Okay. And the mass of chlorine in this is actually asking for magnesium. So the mass of magnesium is 24.21. 31. Okay, so just dividing this. We're going to get an answer of about 25.5%. Okay, so you can do the same for any percent composition problem. Okay. Okay, moving on, looking at purpose of experiment. So earlier, like right at the very beginning of this, I said to think about how these labs reinforce what you know about moles or reinforce what you've been practicing on worksheets, okay? So I'll give you guys a hint on any of these purpose questions. At the front, it gives you the objectives. Okay, the objectives are what you're going to do, okay? What the lab is asking you to do, what procedure you're going to follow to get a certain result, okay? Purpose for me is why. Okay, so you want to look at objectives, compare that to purpose, and hopefully you guys can come up with something like that, knowing that I'm trying to help you guys learn about moles and learn how to use this stuff and not just kind of be able to for an exam. Okay, so I want you guys to learn. So think about how the objectives help you with a purpose. Okay, moving on a little bit. Let's look at data. So you guys should have filled in some data, something like this. This is my data from my experiment. So I took the mass of the evaporating dish before, when it was dry and clean and everything like that, so that I could get the mass of magnesium later, and get eventually, when I'm all done, I didn't actually have to heat it again. Okay, eventually when I'm all done, when I've heated it a bunch of times to get all the water of hydration out of there, so that eventually I can find the mass of magnesium chloride. And that's what this lab is asking you to do, is to compare, to ask how much magnesium is needed for how much magnesium chloride. Okay? So these two numbers are what I'm going to be using. Well, 3 technically. But I'm going to be using these 3 numbers when I move on. The mass of the evaporating dish, when it's just been warming, this doesn't mean anything. These are all my heating, you know, as it drops and doesn't really stay the same. I've got to get it to a point, like we did a while ago, we've got to get to a point where it agrees to within 0.03 grams. Okay? And let's see what else. We've got one more little part here. Okay, it's observations. So you guys know what it looked like when you're adding magnesium chloride to it. I think it's one that I told you to do under the hood or under a watch glass, so you're not breathing in any hydrogen gas. I think Pruitt and Liz and I discovered what happens when you try to light the hydrogen gas on fire and it doesn't catch on fire right away. So hopefully nothing like that happened while I was around, or not getting sidetracked. And so then you guys wanted to note what it looked like when it was dry and everything had reacted. Some of you might not have added enough hydrochloric acid. And you'll note what it looks like, or what it looked like, what your product looked like the day after when you hadn't added enough hydrochloric acid. So for this calculations part, I'm going to skip down to question number 5. Actually, I'll do question number 2. I lied. I'll do question number 2. I'm going to skip around. So for question number 2, you have a certain mass of magnesium that reacted, and my mass happens to be 1.15. Do be sure that you guys are showing all your work on this stuff so that I know you're not just copying it from somebody, and so I know that you understand what you're doing, at least somewhat. Anyway, so that's my mass of magnesium. So I want to know the moles of magnesium that reacted in my sample. Okay, so my sample is 1.15 grams. I've got to look at it in terms of a mole ratio, which I asked myself how many grams are in one whole mole of magnesium, which we just looked at was 24.31. Okay, this is my method of doing this. If you have another way that you think about it, it is certainly fine as long as I understand your train of thought. Okay, so I'm going to do this divided by this, grams cancel, and I'm left with an answer in moles. Now, just looking at this, something on my shoulder. Just looking at this, I mean, how many moles do I have? Do I have more than 1 mole or less than 1 mole? I think I've set this up well because 1 whole mole weighs 24 grams, and I only have about 1 gram, so I think I have a lot less than a mole. So I'll do the math real quick on the calculator. And I find that I have 0.0473. Okay, and that's exactly what I thought, about 1/24. Okay, let's do number 5 as well. So number 5 is asking how many moles of chlorine reacted, and you can calculate chlorine by subtracting number 1 from number 3. Okay, so then we get magnesium chloride minus magnesium, and we get grams of chlorine, which I had as 3.35. That means right here. 3.35 grams of chlorine. Okay, and so then I do the same thing. I look at my mole ratio. I say that 1 mole has 35.45 grams of chlorine in it. Okay, and I'm going to start writing the thing that I'm talking about, what element I'm talking about, so that I can keep track of what's going on. So let's see, that gives me, well, let's see, 3 divided by 30. I'm going to get some number around 9. Well, I mean, a decimal of 9, but 9. So we get 0.0946 moles. Okay, so now I'm looking at a ratio of magnesium to chloride that is 0.04 moles per 0.09 moles. So using these results, I'm going to change colors, using the results from 2 and 5, oops, 5, draw that, uh-oh, opening something. Okay. Okay, so using the numbers I have, using calculations 2 and 5, it's asking me to determine the ratio of chlorine to magnesium in magnesium chloride, and then write the formula. So it's asking for chlorine to magnesium, so I'm going to take chlorine, which is 0.0946 moles chlorine, and divide it by 0.0473 moles of magnesium. So then I end up with a ratio. My ratio is actually not going to have any units because moles cancel, and I end up with so many chlorine atoms per so many magnesium atoms. We can think about that in terms of moles or atoms. Either way, it helps us build our formula. So this number ends up being about, actually almost exactly 2. Okay, so it's 2 chlorines per 1 magnesium. Okay, so if you are dividing a big number by a small number, it's that number to 1. Okay, so I mean, what we figured out in the pre-lab was MgCl2, and my math says that it's definitely magnesium chloride, MgCl2. Okay, I mean, I understand I did this, really meticulously and know how to do the lab, but you guys should be able to come up with a solution similar to this. So if you're seeing some crazy number that's like way out there, you guys, it's on you to figure out where you may have went wrong in the lab and not so much in the calculations, because if you know how to do the calculations, you definitely could have gone wrong in the lab stuff. So, okay, so this, number 1 in analysis and conclusions is where I want you to explain where maybe you didn't come up with a 2-to-1 ratio for chlorine to magnesium. It happens. And they're asking you to explain why you might come up with an experimental error in magnesium chloride versus in just pure magnesium. So think about it in terms of magnesium being a pure element and magnesium chloride being a reaction that you have to, it kind of has to be perfect. So think about that, and that is that. Yeah. So the same goes for question number 2. They want you to compare your experimental percent magnesium, which I came up with as 25.5%, to your theoretical percent that you calculated, vice versa, I'm reading it wrong. Your experimental error you got in question number 7 for your calculations, and your theoretical, what it technically should be according to the textbook, in question 4 for the pre-lab. So they want you to compare that. It really just builds on the previous question, asking you to look at the theoretical percent and the experimental percent and figure out some cause for error in there, which there's all kinds of different reasons. So as long as it's laboratory sound, as long as it makes sense that you could have made this error, or if I definitely saw you make this error, I want you to talk about it, okay? And they give you a certain number of lines for you to write on, so use that as a good judge of how much I want you to write. Okay, and hopefully tomorrow or next class, for this question number 3, it says compare class results to theoretical, and compare whether or not those are random errors, if everybody's making the same mistake, or if it seems that everyone kind of has the same percent. So I want you to look at whether or not, I would compare yours and your table mates and maybe one other group, see if you guys made the same errors or if there's actually some specific thing that we've been doing wrong. I'd love to know if it happens to be something that everyone's been doing wrong. If you really need to know, because maybe there's something in the lab that the procedure says do it this way, and that sets you guys all in the wrong direction to get 30% instead of 25%. So think about what the maximum percent yield is for this reaction, and also suggest ways this experiment could be improved. I think I mentioned when you guys are cleaning up over in the fume hood that the salt, if it had a yellow tint to it, it means there was too much hydrochloric acid. So I would wonder if there's a way that we could improve not adding just enough hydrochloric acid to dissolve all the magnesium, but not too much. So think about ways besides mine that you could improve this experiment, and lab report sheet number 4.1 is finished. Okay, so let's look at moles of iron and copper experiment 4.2, the first lab that you did, but hopefully not the first lab report that you did. First question, actually, I just want to remind you guys again, like, how is this reinforcing what you know about moles? Especially considering you just went through 4.1. 4.2 kind of says, all right, you did 4.1, so let's see if you can handle doing these calculations by yourself. And figuring out what reaction happened and all that. So just to start, I will write out the reaction at the top. Okay, you guys had copper chloride, it was copper 2 chloride, and you added iron to it, solid iron. Oh, okay. Sorry. Okay, Okay, so just looking at this, a lot of you were able to identify this is a single replacement reaction. Iron's going to come in and kick out copper. We haven't discussed why, but what I will say is that the activity series that you're going to have for your midterm explains, lists metals in order of how reactive they are, how likely they are to kick another metal out of a compound. Okay, we haven't discussed that. You don't have the activity series. I'll give it to you for this, so if I ask you whether or not reaction will occur, you'll be able to look at that activity series and see whether or not something's more reactive than the other. Okay, so anyway, a lot of you could identify this with single replacement. So we produce iron chloride of some kind and solid copper. Okay, so what we're trying to figure out here is whether or not we've produced iron 2 chloride or iron 3 chloride. Okay, put a little or in there. Okay, we're trying to figure out which one of these is produced in this reaction. So we can use a mole ratio. How many moles of iron kick out how many moles of copper? Okay, and if it's a 1-to-1 ratio, we're proving that it's iron chloride 2 because there's 1 and 1, and this is a nice balanced equation. Everything works out nice. If it's iron chloride 3, then we end up with a weird equation. Copper chloride plus iron. We end up with this weird equation that says, well, there's 3 chlorides here and 2 chlorides here, so we've got to balance it like this. Let's see, 3 and 2, so then 2 and 3. So then what this is saying is that 2 irons come in and kick out 3 coppers, so you guys would get a really crazy weird number for something like this. So, I mean, really, you would get, let's see, 2 irons come in and kick 3 coppers out, so you'd get something kind of like 3 to 2, but I don't even know. I haven't seen anything like that. It would be really weird. Okay, so knowing that we're trying to prove, that this is the reaction that occurs, let's do some pre-lab questions. How many moles are present in a sample of 34 grams of iron metal? Well, I have 34.0 grams of iron. I can multiply that by my lovely mole ratio, which says that I have 55.85 grams in 1 mole. And I believe it gives me an answer of 0.6. Double check that. Yeah. 0.609 moles. I agree with that because I have 34 grams and 1 mole weighs about 55, so I agree with having about 2/3. Mass of 1 mole of copper, look on your periodic table. Okay, so let's skip and look at the data and observations for this lab, for lab 4.2. Your data and your observations, I mean, I gotta know what you guys saw, what was happening, okay? So make sure that your data table includes observations in some way. But otherwise, your data table, I mean, the little answer key that I've been looking at doesn't even show me a data table, so it's really however you want to organize the information that you understand it. But the most important data for you to have collected, I mean, really everything, but the most important data to have been collected was the mass of the nails before and after, and then mass of the beaker, and that's with and without copper. That's copper solid. Okay, that's copper, not copper chloride. Okay, we don't really care about copper chloride. That just kind of goes into the reaction and helps things happen. But we want to know, think about what I was explaining with the single replacement. We want to know, for the mass of nails before and after, that's telling us how much iron went into the reaction to make iron chloride. And then copper, the amount of copper is telling us how much copper got kicked out and was left as a solid in the bottom of that beaker. Okay, so we should have really 4 sets of data to work with. So knowing that, the calculations are asking us, in the experiment, you need to obtain a ratio of the moles of iron to the moles of copper, okay? That's how you figure out the formula of iron chloride that's used. So what calculations are you going to need to do in order to get the ratio? This has to do it on a separate piece of paper. I'm going to write it out right here, kind of, hopefully not too messy, but okay, so we're trying to figure out the moles of iron to the moles of copper. So let's say, I mean, I gotta find, I don't really have any data myself, so I'm gonna have to make up some data. Let's say I've got 1.5 grams of iron. Okay, so here's my iron calculations. Okay, this is how many grams of iron I have. And then we'll do copper down here. So this is how many grams of iron. How many moles is that? It goes back to the same thing we just did. So we need to divide it by grams, which is 55.85 times 1 mole. Alright, so that's going to give us number 1.5 divided by 55.85. And then let's say I've got copper is 1.8 grams, okay? So that's going to be times the same thing, 1 mole. Only we're talking about copper, so it's going to be 63.55 grams. Let me quickly do that math. Alright, so this is step 1 for iron and copper. So step 1 for this, I mean I can label it as step 1. Step 1 is identifying how many moles I had in my reaction. So this number makes sense because if 1 whole mole weighs 55.85 and I only have 1.5, then I'm going to have a pretty small number of moles for both of them really. So then we've got to come up with a mole ratio to say, is it 1-to-1? Does 1 iron kick 1 copper out, or is it something crazy? So step number 2 is taking moles of iron, 6 moles of iron, and dividing it by moles of copper. Okay, and we end up with a ratio. I will do that math. I've got an idea of what it is. Divided by 0.028. About 9.93 to 1. Okay? I'm going to round that and say that it's actually 1-to-1, because that looks pretty good. I mean, considering I made up this data on the spot so you guys could see what's going on, this experiment tells me that, yes, I made iron chloride because I took iron and copper chloride, copper 2 chloride, and produced iron chloride. Iron 2 chloride and copper. Okay, it says that 1 iron, I'll change color again. It says that 1 iron, 1 mole, came in and kicked out 1 mole of copper to leave 1 mole of iron here and 1 mole of copper out here. Okay, so that's pretty good data. So then what you're going to do with those calculations is write about why you think the ratio is 1-to-1 and why you think that you made, this is for analysis conclusions number 1. Okay, based on the results of your experiment, which form of iron chloride was produced? Explain your answer. So I've explained to you 2 separate times that the ratio is 1-to-1 and you've produced iron chloride. Okay, so it's on you guys to explain why your results do show that or don't show that, and explain that to me, okay? It doesn't tell you to elaborate, but I'm telling you to because I've just told you what the correct answer is. So I need you guys to go a little step further and say why your results do or don't agree with that, okay? Okay, so moving on to question number 2 in the analysis and conclusion section, it's asking you to write a word equation summarizing the reaction. So I've given you the formula, the chemical equation. I'm not writing this very well. So I've given you this. So it's asking you to make a word equation which says I took iron and copper chloride. Okay, so it's asking you to write it out as a sentence, explaining, summarizing the reaction, what happened in it. So I took iron nails and put them in copper chloride, and this happened, and it was awesome. Okay, feel free to elaborate as such. For number 3, it's asking in the other direction, if we took small pieces of copper with some iron chloride, would the same reaction happen? Okay, this has to do with the activity series that I mentioned. Okay, that will help you a lot in answering this question. Same is true for question number 1 down here on the synthesis part. Oh, I think it's going to open something again. It better not. Okay, I think I figured out what I wanted. So, maybe not. Why does the reaction of iron and copper chloride occur? So it says, review the activity series. You guys don't have chapter 3, but you can certainly take a glance at an activity series online and see how copper and iron compare to each other on this activity series. Okay? And so if you're answering why the reaction of iron and copper occur, then you're actually answering why this will not occur. Okay? So, and why shipbuilders put pieces of zinc on the hulls of iron ships? I did not know this before I started doing this lab with you guys. So I will have you guys look it up. Okay? If you want, you can write a guess. Then Google it. Okay, so I know what your train of thought was. So you just write like what you think maybe, why they put zinc, and then Google it with the right answer. And so then I can see the comparison of what you were thinking and whether or not you were right. So that brings us to the end of Lab 4.2. Yay! Okay, so now we're going to look at moles and mass in a reaction, experiment 5.1. First thing I want to do is, again, read the objectives to you guys, where I'll remind you again that we're looking at moles, and we've got to look at moles in terms of mass. Something I may not have said before, and I apologize if I haven't, but we're going to get into this after this midterm. You have to go through moles. Everything you do in chemistry, from this point on, you can't have grams of something and get to grams of something else without going to moles, and back out to grams again. Okay, I will give you guys this like organizational chart. It's like the land of the moles. Okay, so you can't go from one thing to another without passing through moles. Okay, you guys may be discovering this as you're doing some of these lab questions, that you are getting wrong answers because you're thinking that, well, I have grams of this and I have grams of that, so it just transfers. But it really doesn't, because moles of one substance don't weigh the same amount as moles of another substance. So I'll reiterate again, you've got to look at this lab and all the other labs in terms of how it helps you understand and reinforce that fact that moles are everything. Okay? Everything goes through moles. Moles suck, but you know, once you understand them, it works in your favor. It works awesome. Okay? So let's look at the objectives for moles and mass in a reaction, which is experiment 5.1. Observe a reaction between hydrochloric acid and sodium hydrogen carbonate. In your calculations and observations, I want to know what you saw happening and what was going on, what you saw. Hopefully you read through the introduction here, where it talks about carbonates and what happens in carbonates and what kind of scientist makes reactions with carbonates, things like that. So it talks a lot about these kind of reactions, so you should be able to make good observations based on the introduction here. The other thing you want to do is calculate the number of moles of sodium hydrogen carbonate and relate that value to the number of moles of sodium chloride that are produced in the reaction. So we're going to be looking at your reaction and a theoretical reaction, which is what we've been doing before these labs, where we were doing balancing equations and things like that, and just kind of looking at theoretically, if we have this much of something, how much of this is going to be produced, okay? So law of conservation of matter, matter cannot be created or destroyed, so if you have 2 of this, you have to have 2 of that on the other side, so, or excuse me, 2 of this, then there has to be 2 of this on the other side, even if it's in a different form or in a different chemical, okay? Then you're going to calculate the moles of hydrochloric acid used in the reaction and the moles of water and carbon dioxide produced. Those are straight up questions in the post lab, so if you don't reach those objectives, then you didn't do the work. And you're also going to determine the mass of reactants and products, so how much everything weighed, even if you couldn't capture it. So carbon dioxide escaped from this reaction, as did water, because everything evaporated. But because you know weights and amounts of other things, you can calculate the masses of those, and also because you know the moles of things. So moving on, let's take a look at a couple pre-lab questions. The only thing I want to say about at least the first two is, did you read the introduction? So, 1 and 2 are right in the introduction. So, reading through it, I want you guys to realize that a reaction between sodium hydrogen carbonate and hydrochloric acid is a double replacement reaction. But it produces 3 products because of the carbonate that's involved. And that's what the introduction is telling you about, okay? Hydrogen carbonate breaks down very quickly into 2 additional products, okay? And it very clearly tells you this, okay? And you have to work with this type of reaction for the entire lab. So make sure that you read through that introduction so you get these 2 answers correct. Okay, so here's my data. This is from my experiment from a while ago. We've got to look at, so if we're looking at the mass of the beaker, okay, there's very little data that you guys needed from this lab. So you needed the mass of the beaker, the mass of the sodium hydrogen carbonate that you put into the beaker, and then the dry solid that shows up a couple days later when you guys are doing this. So the dry solid actually happens to be sodium chloride, okay, and calculating the mass of that, pretty simple, this minus that, and you combine, I get 2.11. And then the mass of the sodium hydrogen carbonate I got as 3.10. Okay, so I'm going to use these masses, okay, calculate the masses up. It's talking about your data. Okay, I saw a lot of people kind of calculating the masses of 1 mole, but it doesn't say calculate the mass of 1 mole. It says calculate the masses up. So I would naturally assume that it means these up here. So make sure that you're doing calculations based on your own data. Okay, so I had masses of 3.10 and 2.11. So calculating the number of moles. Now, I mean, it's the same thing we've done over and over again. I'm just going to do one of them again. The mass of, the number of moles of sodium hydrogen carbonate, we take the grams, we multiply it by our mole ratio, which says in 1 mole of sodium hydrogen carbonate, which means we've got to look at sodium plus hydrogen plus carbonate, which is going to be sodium plus hydrogen plus carbon plus 3 oxygens. Okay, and that's 84 grams, so let's go with 84.0 grams. Okay, giving me a total mole value of about 0.0369. Okay, same for this. Okay, now the balanced equation, you guys have to think about, you started with sodium hydrogen carbonate. Okay, now they're going to give you stuff like this. They're going to give you stuff that's already correct and neutral. Okay, so don't worry about trying to figure out charges and stuff in here. It's already neutral. Okay, and I mentioned earlier that this is definitely a double replacement. You got to look at hydrogen carbonate as one thing and chlorine as another negative. Okay, so here's our 2 anions. Okay, so those are going to come together. Our 2, oh yeah, so I said that wrong. Those are our 2 anions. So those are going to participate in the double replacement, the switch. So we've got chlorine is going to join with sodium, making table salt. And then we are left with hydrogen carbonate and hydrogen. So that actually makes H2CO3, but this is the product that ends up breaking down into 2 individual products. Okay, so that's on you guys to figure that out. Then balance it. Okay, so if you balanced your equation correctly, you'll be able to come up with a ratio of moles of sodium hydrogen carbonate to moles of sodium chloride. Just remember that when you're doing something like this, when you're comparing these in an equation, it's 1 if it's not there. Okay, so if you wrote sodium hydrogen carbonate plus 2 HCl, make something, okay, CO3. If you wrote this, then this blank space here actually represents 1. So this, we've got to think about these in terms of moles. So this would be 1 mole, and this would be 2 moles. Okay, so when you're doing your ratio, make sure you're thinking about this. And then comparing your answer would be taking what you got from question 2. Question 2 had part A and part B. Okay, so you're going to divide those moles by each other to come up with some ratio to 1. Okay, so you're going to compare this one to this ratio down here, okay, using question 2. Okay, hopefully it's similar. Hopefully. Okay? Using the value you obtained for the number of moles of sodium chloride produced. So let's look at my numbers. Where's my number? Number of moles of sodium chloride. So I'm going to underline that. Number of moles of sodium chloride. Okay, so I actually had let's see if we can look back a little bit. 0.0361. Okay, so that's how many moles I had produced. So it's asking, we got to do this math twice. We're looking for moles of carbon dioxide and moles of water that would have been produced. So we've got to do 2 different series, 2 different sets of math problems here. They're actually really simple, but they prepare you for what we're going to be doing with moles, you know, and I said everything goes through moles, so you can't just say I have 1 mole of this, so I have 1 mole of that. Okay? Not all the time. Okay? For this particular example, you can. Now I'm going to do 1. I'm going to say for water, I've got 0.0361 moles of sodium chloride. Now, this is where, at this point, right here, question number 6, this is where you want to start writing down the element or compound that you're talking about. Because if you don't, it's going to get really confusing really fast. Okay? I really hope every single one of you takes this to heart. Write it down somewhere. Start writing down the element or compound that you're talking about when you're writing out these dimensional analysis problems. Okay? So I've got this many moles of sodium chloride, and I'm going to look at a ratio that is, I'm comparing sodium chloride to water. So I know that I want to solve for water. I want to solve for moles of water. And I have moles of sodium chloride, so I actually want to get those to cancel. Okay? And if I look back on my balanced equation, I will find how many moles of water, which happen to be 1. Okay? So again, like I said before, this ends up being a simple problem, but it won't be in the future. So you need this step so that we can cancel. I'm going to do a different color again. You need this step so we can cancel moles of sodium chloride to solve for moles of water, which ends up being the same number, yes. But it won't always be the same number because we won't necessarily stop at this point here. Okay? Same question for number 7. Okay, it's really asking you for all of these, it's asking you how much, let's see, I want to make sure number 7, yeah. So for 6 and 7, it's asking you how many moles of carbon dioxide, how many moles of water, and how many moles of hydrochloric acid. Okay? So it wants all 3 of those things based on the number of moles of sodium chloride you produced. Okay, so it's not based on my numbers, it's how many you produced. Okay? Okay, I will talk a little bit about the synthesis questions here. We're still on 5.1. A similar reaction occurs between limestone, which is calcium carbonate, which the calcium is +2 charge, and carbonate is -2 as well, and hydrochloric acid, which is HCl, as we've been working with. Okay? They want you to write a balanced equation for this. Okay? I'm not going to write the balanced equation for you. It's a carbonate, so we can guess that there's probably going to be 3 products. We've seen it a couple times. Okay? So using that balanced equation, we've got to duck out, and we've got to do the same thing we just did before. But the first thing we have to do is, since we have 3 grams of limestone, okay, we want to know what mass is. Now, again, we can't just go from 3 grams of limestone to grams of something else in the reaction. We have to go grams of limestone to moles of limestone to moles of calcium chloride to grams of calcium chloride. Okay, so what I'm going to do is first convert 3 grams. I'm going to do it down here. Okay, I'll do it in a different color too. We're going to convert 3 grams of limestone, which is calcium carbonate, to moles. And again, it's the same thing we've been doing a few times, doing quite a bit. Calcium carbonate, it actually happens to weigh 100, which is calcium plus carbon plus 3 oxygens, and that's in 1 mole. Okay, which we get a number that is 0.03 moles of calcium carbonate. Okay, so with that number, we can solve A, B, and C. Okay, and I think, yeah, just click. So let's do a color again. I'll do it in red. Now, I haven't done this balanced equation up. I haven't done the balanced equation for number 1. So it's on you guys to get the balanced equation and figure out how many moles of calcium carbonate and how many moles of hydrochloric acid are needed for this reaction. Once you know that, you know how many grams and how many moles are going to be put into this equation. So I will give you the basic outline for it, and then you guys can go about solving A, B, and C. Okay, so we know that we have 3 moles of calcium carbonate. That's the sample. So I'd like to start with the sample that we have, which is 0.03 moles calcium carbonate. I don't know if you're sick of me saying it yet, but I'll say it again. You desperately want to start writing what it is you're talking about. Okay, what element, what compound, what molecule, whatever. Okay, you desperately need to start writing that, okay? So that's what we have. Okay, and if you want, you can write that over 1, which is our 1 sample, if it helps you keep you straight. And so we're looking at, if this is how many moles of calcium carbonate there are in our sample, what can we multiply that by to get over to calcium chloride? We've got to use the mole ratio. And so in your balanced equation, you find some amount of moles divided by some amount of calcium carbonate, moles, calcium chloride. Okay, so we did this step before. Okay, it's very simple, but what we're looking at is saying if we have 0.03 moles of calcium carbonate, how many moles of calcium chloride do we have based on the balanced equation? Okay, so this cancels now. And we can move on. What we have left with this is 0.03 moles of calcium chloride. Okay, that's if it's 1. We don't actually know, until you guys balance the equation, you don't know what these numbers are. Okay, so you're going to fill this in. That's why I put question marks. Okay, now the next step would be we've got to get back into masses. So we've got to divide by moles, right? We've got to say, okay, we've got to multiply. We went back here. Back here we used a mole ratio, so we can use a mole ratio here too. And we're talking in terms of grams of calcium chloride over moles of calcium chloride. Okay, it gets tedious, but it's totally worth it to do this and write all of these out. Okay, and let's see, calcium chloride. I just wrote this number down. I think it happens to be around 111. Okay, that's 111 grams, which is calcium plus chlorine times 2. Okay, so it's 40 plus 35 plus 35 or so, somewhere around there. Okay, so that now, using different color, we cancel moles here again. We cancel calcium chloride again, leaving us with exactly what we want, which is the mass of calcium chloride. Okay, and I'll let you guys do the math. Hopefully you guys come to an answer that's hard to say, because we need to know what these are here. Oops, I didn't draw. Okay, we don't know what these are. Okay, once you have a balanced equation, you can do this. And so it's going to be 0.03 times something divided by something times 111 equals grams of calcium chloride. Okay, hopefully that points you in the right direction enough to do A, B, and C. So I'll let this sit for a second so you guys can copy it down, pause it if you need to. Okay, so now what I want to do is just quickly show you guys the other page here. So the other thing it's asking you is for carbon dioxide. So you're going to use that same, oops. You're going to use the same ratio. Let me just double check it again. Okay. You're going to use the same moles of calcium carbonate for each of these questions. Okay, multiply it times and so on. Okay, and the same here. Okay, because the moles of calcium carbonate doesn't change in this sample. That's what you started with. So again, with law of conservation of matter, nothing can be created or destroyed. So you always have this amount, okay, to start, and so that is going to show up in other places on the other side for products and other reactants. Okay, balanced equation for reaction of vinegars, which is acetic acid. So that's going to be HCHO232 with baking soda, which I have helped a couple people with this, and I never remember which it is, but it's sodium bicarbonate or sodium hydrogen carbonate, so it's NaHCO3. Okay? And that's another carbonate reaction, so you're going to have 3 products. Okay? Now, just because there's 3 products doesn't mean it's not a double replacement reaction. All right, so now we're looking at calculations with a chemical reaction, experiment 5.2. This one starts to deal a little bit with molarity, and I truly apologize, because I really wanted to kind of get you guys into molarity by now so that that italic M right here, that it wouldn't be an issue. But here I am. I'm going to give you every answer exactly as I know it to be for anything that involves molarity, because I don't want you guys to get confused. Please, I'm going to write this right here. Molarity, not on midterm. Okay? You are responsible for molarity on these lab reports, but here, for these labs in particular, I definitely want to make sure I give you guys all the answers for molarity so that you're not confused. But know that molarity is not going to be on the midterm. We are going to deal with it a lot, but it's not going to be on the midterm. Okay? So backing up, I want to look at the objectives for this lab for experiment 5.2. We're dealing with calculations in a chemical reaction, which there were a lot of calculations in this lab. This one was the one where you're working with the little pipettes and filling them completely and figuring out the volume and the capacity of them. So once you've done that, you're looking at observing the reaction between solutions of calcium chloride and sodium carbonate. Many of you noticed that there was a precipitate formed, okay, almost immediately, because we have done the aqueous solutions lab, and I know that's like evil, that's a horrible thing of me to mention and bring up again, but I will note that all of you that turned in the makeup for that, your grades jumped like 40% or higher. Like they just jumped a huge amount, and it was totally worth it. And I think a lot of you that turned it in and resubmitted it really understood what the point of it was and understood the stuff behind it. So hopefully that helps you move forward in chemistry and really understand what you're doing. So well, let me just jump off my soapbox and come back to explaining objectives for this lab. You're also going to calculate the number of moles of each reactant present and determine the reactant that is in excess. Now, in the previous labs, you've been doing this. You've been taking a mass, which you can easily get on a scale, and converting that into moles. So we're going to do the same thing here, but we're going to look at which reactant you put too much of in so that you would have, and so that you would completely react to the other reactants. Okay. The other thing is the theoretical yield of calcium carbonate and compare it to an actual amount produced, and then calculate your percent yield. Okay. I will talk about that a little more as we get to it, but for now, let's look at the pre-lab questions. Okay. So the first one asks you, it looks at molarity, and I've written this down for a couple people. The capital M is molarity. Okay, and molarity basically means the number of moles per liter of solution. Okay, it's dealing with in terms of it's looking at moles and solutions in terms of their concentration. So something that is more concentrated, like you guys see me drinking my Mio a lot. If I put 3 squirts of Mio, then I have more moles of Mio per liter of water than I do if I only put 1 squirt of Mio. Okay? Hopefully that's simple. We're going to work on molarity after the midterm so we can get a better understanding of that. But for this, if you know that it's moles per liter, I'm going to do this in the long form. If you know that molarity is moles per liter, then you can figure out how many moles are in a sample of sodium chloride that's 22 mils. Okay? So we got 22 mils. We need to get mils to liters because we have liters over here. So let's see, 1 liter has 1,000 mils. And we're dealing with a 0.5 molar solution. So if we take 0.5, we have to break that M down into moles per liter. So it's going to be 0.5 moles per liter. And in a different color, we cancel mils, liters, and we're left with an answer in terms of moles, which I didn't really leave myself room to write an answer. I'll put it over here. It happens to be 0.0110. Right there. 0.0110 moles. Okay, so that's how many moles are present in 22 milliliters of a half molar solution. Okay, you get some more practice with this. Hopefully the math makes sense going across. You're taking milliliters, getting it into liters, and then looking at its concentration level, which is only half a mole. So that's not actually very concentrated. So in a small sample, so in 22 milliliters of a liter, there's going to be a very small amount of moles. Number 2, you have done, oh come on now, there you go. Number 2, we've done a million times, so I'll leave that to you guys. Writing formulas, you're going to see this on the midterm. I gave you guys worksheets for you guys to practice on. If you complete those, 1, it will give you lots of good practice if you're doing them correctly, and 2, if you turn them into me, I'll give you 5 extra credit points on your midterm. So build these using your ion formula chart. Okay, and you should have no problem with those. Okay, so for this particular lab, for 5.2, I've skipped a bunch of questions. The rest of the pre-lab questions and that are really easy to answer if you look at the introduction or look up some definitions. If you have any questions, ask me. We've got a little more time to work on these, so if you're still unsure about some of those pre-lab questions, just ask. But otherwise, I'm not too concerned. So I want to move on to, I'm not going to show you my data for this. I'm just going to do the calculations and hope that you can follow along with me with what I'm doing. To find the mass of the water in the pipette, you took the mass of the pipette and then the mass of the water and the pipette, so you do some subtraction and you find that it weighs 4.53, mine does, 4.53 grams. Okay, so hopefully you guys come up with a number similar to that. The pipette should have about the same volume and about the same mass of water in them. So then, solving the volume of water contained in that, please make sure you show your work. Okay? When they provide you with all this space here to answer a question, it means they and I want you to show your work because there should be some calculation involved. So you've got the mass. Okay, I'm going to write a little arrow like this. You know that the density of water is 1 at room temperature, which is what we're working with. And so 1 is equal to 4.53 grams over volume. So in order for this volume, in order for our number on this side to equal 1, what does volume have to be? It has to be 4.53 grams. Okay? Oh, excuse me. Not grams. Mils. I'm going to call it mils. I don't like that they use centimeters cubed. So then the volume of the pipette is going to be, as it says here, the same as above, 4.53 mils, or whatever your number happens to be. And then they want to know the volume of the sodium carbonate solution that you use. It has to be the same volume too. And some of you had some confusion with that, but just because, whether I have water or Mio or milk or milkshake in here, it's not taking up a different volume in this. It's a different weight, yes, so it's a different density, but it's still taking up the same amount of volume as long as I've filled it completely, okay? So with that, my volume of sodium carbonate is also 4.53, but the calcium chloride, if you look back in the procedure, you use 2 volumes. So you're going to multiply this number, and it's going to be 9, closer to 10, yeah, okay, 9. They round it, I don't like that. Let's call it 9.06 mils, okay? So that's the volume of the calcium chloride because we use 2 volumes of it, so you've got to do a little multiplication. Okay. Let's see, where, I gotta look at my numbers here. So, now this is, again, I'll circle them, 6 and 7. Oops, come on, 6 and 7. These deal with molarity, okay, which is like italic M. Alright, so these ones, I don't expect you to know how to do this. I'm really excited if you do, because you're putting like some concepts together, and I'm really proud of you. But again, I'm not expecting miracles, so I'm going to explain this to you for both of them. Moles of sodium carbonate. We started with volume. That's all we have. That's all we know, because we have a solution of sodium carbonate. And we started with 4.5 mils. Okay? I'm rounding down a little bit to make it more simple. And then we gotta go back, because moles are, molarity is moles per liter, so we've got to get to liters, okay? And then, so now we've got, all we have is this number in terms of liters, so then we've got to look at it in terms of moles, okay? And we got to get to moles per liter, okay, which is molarity. Again, molarity, capital M. And I gave you guys a solution that was 0.6. Let me just double check in the lab manual here. 0.6. Okay, so the solution of sodium carbonate that we used was 0.6 molar, okay, or had a 0.6 molarity. So that's 0.6 moles per 1 liter. So that gives us a nice answer of 0.0027. Moles. Okay, now this is my answer. You guys can do this with your data, with your stuff right here, with your answers you got here, with your volumes and stuff. I would love it. I really want you to. Even though I don't expect you to understand moles as a concept, I definitely want you guys to do this calculation with your own numbers. Okay? Same for this one. Moles of calcium chloride. We know that we had 9 mils. And I'm actually going to skip a step here and say that it's in 1,000 mils, there were 0.4 moles. Okay? This is the concentration I used, this here is the concentration I used for the calcium chloride solution. Okay? And you use 2 volumes of it. So I'm skipping some steps. I'm just skipping this step here, really. And that gives us a volume of about 0.0036. Oops, 0.0036 moles. So the next question is asking us the mass of calcium carbonate. That was your dry solid, the white dry solid. So that's going to be the, I mean, I don't have it right in front of me, but it's going to be the mass of the paper. Oops, the mass of the paper with the solid, and then the mass of the paper without the solid, subtracting those. So that for me, my bit of data gives me 0.23 grams, okay? Again, we can really simply go from grams of calcium carbonate to moles of calcium carbonate, because we just multiply it, we have a mole ratio. Calcium carbonate, we actually used that in the previous one, it was limestone, which you guys would be interested to know that calcium carbonate is present in eggshells. But that's about 100 grams, and so we end up with 0.0000, yeah, 23 moles. Okay, so then we can do a balanced equation, and we can look at which reactant was in excess. So balanced equation for you guys. We started with, just double checking, we started with calcium chloride and sodium carbonate. So, sodium carbonate and calcium chloride. And we know we produce calcium carbonate. Oh, what else? Okay, definitely a double replacement. Oh, oops, don't do that. I'll mark it over here. Definitely a double replacement reaction. So, you guys should be able to identify the other product and then balance the equation. Okay, now, we've got to jump back to determine which of the reactants was in excess. We've got to look back, use red. We've got to look back at questions number 6 and 7. Let me just double check that it is 6 and 7. Okay, so for number 6 and 7, I found that I had 0.0027 moles of sodium carbonate. And I left it at the top up here, 0.0036 moles of calcium chloride. Okay, again, I'm writing down what I'm talking about so I don't get confused. Now, we want to know what reactant was in excess for this reaction. So we're comparing sodium carbonate to calcium chloride. Now, assuming that your reaction is balanced, okay, one of these for whatever this last one is, 1, 1, 1, and whatever. We don't actually care about this. We know that there's going to be this many of these. Okay, so if there's 1 mole of sodium carbonate and 1 mole of calcium chloride, which of these is in excess? Which one of them did we add more of than was necessary? Okay, so for question number 12 and 13, we've got to find 12 before we can find number 13. So for number 12, we're looking at the amount of calcium carbonate. So when they say amount, I always assume grams or a mass. Okay, so we've got to go from the limiting reactant, which I think I'm going to call this number. Okay. Now I'm not going to write down well, I guess I kind of have to. So limiting reactant is this. I'm going to call it A. Okay. Limiting reactant A. We've got to use the mole ratio, so we've got to divide it by moles of A. And we're going to look at moles of B. Okay, and we're talking about theoretically what things should be produced. So if we're, all right, I don't want to get myself I don't want you guys all confused, but we're talking about theoretically what should be produced. So we've got to think about the balanced equation, which says that there's 1 mole of A for 1 mole of B. Okay, and I'm not telling you whether I'm talking about calcium carbonate or sodium carbonate, because you guys have to use what you figured out from questions 10 and 11 to figure out what I'm talking about here. Okay, so we get moles of A, and moles of A to cancel. Okay, then we want to know how many moles in 1 mole of B, mole B, how many grams are in a mole of B. So whatever you guys determine the weight of that to be, then we get moles of B to cancel. And you end up with an answer that's 0.0027 times the gram, which is the molar mass, the grams of B, which gives, well, B is going to be calcium carbonate, because that's what they're asking us, right? They're asking us to calculate the amount of calcium carbonate. So we went from the limiting reactant A to moles of A and B, out to B, which is our calcium carbonate, and we got straight to grams of B, which is grams of calcium carbonate. And so we get 0.0027 times that number of grams, which should give us a theoretical amount, the theoretical amount of calcium carbonate that's produced. So equals grams of B, okay, which is also calcium carbonate. Sorry, I got myself a little confused using A and B, but if you know that calcium carbonate is B, and you figure out what A is, you can figure out the rest of this answer. Okay, and so I'll leave that up for a second so that we can then move on to number 13. Okay, so for question number 13, we're calculating the percent yield. So 100% yield is going to be the answer you got from number 12. Number 12 is 100%. Okay, but what you actually got we're talking about calcium carbonate, so the mass I got, I found that in number 8. I just want to keep this straight for you guys because I can't show all the pages at once. 8, massive calcium carbonate. Number 8 is the percent yield. Okay, so in order to solve, you've got to divide. You've got to take number 8, the answer in grams, divided by the answer in grams for number 12. Okay, which we did solve with the 12 in grams. Yay! Okay? You take that, multiply it by 100, and we get 8%. Possible sources of error, you guys can work on this. You know, if your calcium carbonate, the limestone you produced wasn't completely dry by the time you were weighing it, or if you didn't set up the filter right, there's a lot of different sources of error in this. If it got bumped and stuff, because it's a pretty cramped fume hood under there, there's a lot of sources of error. And so then you want to look at, when you figure out what the percent yield is for your product, you want to look at what would happen to percent yield if you had different amounts. Okay, and you'll see percent yield on the midterm, most likely. Okay, looking at theoretical, if I give you some fake data, you guys should be able to predict what kind of information, you know, if some precipitate remained or if the solution was not clear, etc. Okay? Okay, so after looking over these questions and answering them myself, they all involve molarity. So I'm going to make an executive decision here and tell you that you're not responsible for these three questions. Okay? They all ask you to go for molarity, you know, and all that. So I just don't want you guys to get confused. I'm going to leave it out. I'm sorry. I really am sorry if you guys have already tried to answer these questions. Just erase it from your brain. You are not responsible for these three questions. Okay? You are, however, responsible for question number 4. Circle. Okay? You are responsible for question number 4. How would you recover the sodium chloride from the solution? You've been dealing with calcium carbonate from the solution. So how would you recover the sodium chloride? So picture that little setup where you had a filter paper and you're pouring water through and it's collecting down here. You're collecting the water. Look, it's even blue. So you're collecting all of this liquid down here. Okay, and this is your liquid going through the filter and you're collecting like the white calcium carbonate in here. And you're assuming that sodium ions and calcium, chlorine ions are just floating around in here. Okay, so that's what this question is about. How would you recover the sodium chloride from that solution? And that is the end to experiment number 5-2. Okay, last lab, experiment 5-3, investigating which reactant is in excess. Okay, I hope that you guys read through a little bit of the instruction here because they're you know, there's a little bit of important stuff in there, so hopefully it will help you answer pre-lab questions. But what I want to do right now, as before, is read the objectives to you and discuss. Calculate the number of moles of each reactant. You did that in experiment 5-1 and 5-2, so hopefully at this point in working through the labs, you really understand how to find moles of something when you're given a mass or even a volume. Okay? Predict which reactant is in excess. You did that in the previous question, the previous lab, 5-2. So hopefully it's a little more obvious here by, you know, macroscopically looking at it. So looking at the reactions of zinc and hydrochloric acid and then also doing the calculations of zinc and hydrochloric acid to see which is truly in excess. Okay? And so then you're going to relate macroscopic observations to microscopic events by making drawings of your observations. So let's look at pre-lab question number 1. Pretty basic. Calculate the number of moles in 2.65 grams of zinc. We've done this, what feels like 100 times to me, but probably only a few times to you. So I'm glad to help you guys out and write it over and over again. Let's look at, we've got moles, grams of zinc. Don't have zinc memorized off the top of my head. 65. What? Okay, just double check. 65.4. I thought I read that wrong. Alright, and that gives us, quickly plug in a little math here, 2.65. Oops. A little punchy. 2.65 divided by 65.4 equals, grams cancel, and we get 0.0405, not rounding, 0.5 moles of zinc in 2.65 grams of zinc. Number of moles of hydrochloric acid in 37.5 mils of 3 molar. So I expect you guys to do this calculation along with me because it involves molar or molarity. So we got to take our sample, 37.5 mils, convert it to liters, and then convert that to moles per liter, which is 3 moles per liter. Okay, and that gives us a shiny, nice, neat, and tidy answer of 0.112 moles. How many moles of hydrochloric acid are required to react with 0.244 moles of zinc? Now, when a question is asking you how many moles of this are required to react with that, think about that in terms of a mole ratio, okay? How many of this for how many of that? So I'm going to have to give myself a little bit more room. I'm going to clear this out. You guys can write it down. Pause me if you need to. Write that down. How many moles of hydrochloric acid? So we're given 0.24444 moles of zinc. Okay, now we've got to think about the reaction. So I'm going to kind of squiggle up here and write the reaction. We know that we're taking hydrochloric acid and zinc and reacting them together. Again, a lot of you can identify this really quickly as a single replacement where zinc is more reactive than hydrogen. It's going to kick it out and make zinc chloride. Zinc has a +2 charge in this case. Hydrogen is a diatomic element, Brinkelhoff, so it appears by itself as H2. So now it's not quite balanced. We've got 2 Cl's and 2 H's, so we just quickly put a 2 over here, and we find that for every 2 hydrochloric acids, you need 1 zinc to complete this reaction. Okay, so with that, we can look at, I'm gonna back up again and repeat this. How many moles of hydrochloric acid are required to react with this many moles of zinc? So we've got to look at this as a ratio, which this is how many moles we have. Whoops, not writing this right. This is how many moles we have of zinc. Okay, so we got to put zinc on the bottom. Okay, and we got to think of it in terms of moles. And we set up here is 1 mole of zinc for every 2 moles of hydrochloric acid. Okay, so now I added the multiplication at the end, but do we need to multiply any more? No, I don't think we do at all. So we don't need that. We need equals, which we cancel moles of zinc for moles of zinc, and we end up with moles of hydrochloric acid, which it just doubles, and we end up with 0.488 moles of HCl. Okay, so for 0.244 moles, we need twice that. Okay, and that's because you know how to balance equations. So let's look at part 1 of data and observations for your lab report on 5.3, which is investigating what's in excess. So I'm just going to give you guys a hint. You guys can describe what happens. You did the lab, so you can pretty easily talk about what happened when you were doing this lab. One of the things I will say is that they give you 4 of these things here. So I just wanted to point out that the 4th thing, a lot of you had trouble figuring out what the 4th thing was, is water. Because you're not dealing with pure hydrochloric acid, you're not dealing with pure HCl, so there's going to be water in this as well. Okay, so I just wanted you guys to note that on top of these 3 fairly obvious things, you can add a 4th. Okay, and then the same thing for after. If there's any liquid left at all, you guys can identify this reaction as hydrochloric plus zinc. We've already done this. As zinc chloride plus H2 gas. So the hydrogen gas isn't going to be anywhere near. If there's any liquid left, it's going to be the water. Okay, again, if there's any liquid left, it's going to be the water. If there's any clump here, it's going to be the zinc. And then any other liquid is going to be the zinc chloride, which is an aqueous ionic solution. Okay, let's see if there's any liquid left. Yours might not look exactly like this, but this, theoretically, if you're putting enough chloride in it and you're letting it react for a certain amount of time without it evaporating, this is what you would see. Okay, so then you're going to describe, describe the cup and its contents, and then, sorry, so you're describing it and you're making another drawing, and they actually give you the drawing. I was reading that like it was asking you to make a third drawing, but you have your two drawings right here, so you're all set. Okay, so let's move on. Okay, so I skipped the part where I showed you my data. There is a data table provided for you guys because you have to figure out the mass of the little pipette and then the volume of the water and all that. So I'm going to skip questions 1 and 2 because it's very similar to the lab where you guys calculated that. I don't remember if it was 5.1 or 5.2, even though I just did it. I think it's 5.2. So you just did that. You're also going to use the masses of the cup and zinc to figure out how much zinc you used. And then we've done number 4. We've done number 4 a bunch of times. So you're going to take the grams of zinc times the amount of moles of zinc, which I think I just said was 65. My periodic table I got here, 65.4 grams. Okay? And that gives you an amount of moles of zinc. Okay, so, and for question number 5, the volume of hydrochloric acid, that depends on how many pipettefuls, I'll write that as a question, how many pipettefuls did you use? Did you use for your experiment? It says in the procedure, it says use 1 or 2 full pipettefuls, so it depends on how many you use, so that's calculating the volume. So you're going to use the volume of the pipette here times 2. Okay? Simple enough. Okay, question number 6. We have to use question number 5 because you have a volume. Okay? Now this is definitely a molarity question, so I'm not expecting you guys to 100% know how to do this. So what we use for our molarity of HCl, I'll just do out this problem. How's that? Let's see, we've got a volume, which I'm going to say my volume is about 9.1, and that's per 1,000 mils because we're using molarity. And we used 1 mole, 1 molarity. So that M is actually 1, okay, capital M. So this is how many moles of hydrochloric acid. I just don't want to do math at this point. 0.0091 moles. Okay, so that's how many moles are present, how many moles of hydrochloric acid are used. Okay, and in the previous question, you figured out how many moles of zinc. Okay, I didn't do that problem out because I didn't use any data for this. So let's say I've got, and this is moles of hydrochloric acid. So let's say I've got like 0.0072 moles of zinc. Okay, this is, you need both of these numbers to figure out the answer for number 7. Okay, which reactant is in excess? If you know that you need HCl, 2 HCl's for every 1 zinc, which is in excess? Okay? And that's the last question for calculation. So moving on to the analysis and conclusion questions, which there's only 4 questions left in this little review here. Question number 1 is asking you guys, I'm going to change colors. Question number 1 is macroscopic observations of the cup. Okay, so based on what you looked at and what you saw in the cup, was there like a little chunk of zinc left? Was there a little bit of liquid and no zinc? Go by what you saw and tell me what reactant is in excess. Okay, so then if you're telling me here, determine which reactant is in excess. Circle this already. Was that prediction you made correct? Okay, so you're predicting back here I think, based on this microscopic, I think that I was right because when I saw up here. Okay, so you're comparing question number 1 with question number 7. Okay. So you're talking about 2 possible explanations for having no zinc left after the reaction. One of those being, let's see, if we're talking about limiting and excess reactants, if there's no zinc left, then maybe you added too much hydrochloric acid to react all of the zinc. So if we're talking about that, if we say that there's too much hydrochloric acid, experimentally, how could you prove this? Okay, so I'm going to leave you guys with this. This is one explanation. You need 2. One explanation here, and I want you guys to respond to this. If you put too much hydrochloric acid in, how can you prove that? I hope that helped.